Okay, welcome everyone. Today we are very happy to have Henry Lee, who's visiting us from Stanford, and he's going to tell us about bootstrapping in matrix quantum mechanics.
Okay, thanks a lot, and I'm happy to be here. Yeah, so this talk is based on a couple of papers with several collaborators, including Minjake's in the audience, Zheng, Barak, and Jessica. Jessica's a graduate student at Stanford. Okay, so just to start with some propaganda, black holes as seen from the outside are described by ordinary quantum systems. So we have some picture like this. And I just wanted to start with a trivial point, which is that it would be nice to solve such a quantum system. And by solve, I mean, for example, computing thermal correlation functions on the left-hand side. Okay, and another historical point is that for certain special black holes, we know explicitly what the quantum system is. For example, it could be a large N quantum mechanics or a large N quantum field theory. And a simple question is, why haven't we solved these black holes yet? Okay, so I think there's at least two reasons why. And the two reasons are both related to the horizon, right? So one aspect of black hole physics is that black holes have a horizon. The horizon is associated with an entropy. And the important thing about this formula is that G Newton is in the denominator of this formula, right? So in the semi-classical limit, G Newton is small and the entropy is very large. So that implies that we need large N if we want to solve a quantum system that's related to a semi-classical black hole. And the second reason, which we're now somewhat more familiar with in a modern language, is that black holes, as described by general relativity, are maximally chaotic quantum systems. Okay, and that's related again to a simple feature of the horizon. If you study a particle falling towards the horizon, its momentum grows exponentially. Okay, so that exponent is related to the chaos exponent. Okay, so this maximally chaotic nature of black holes means that the dual quantum system is going to be strongly coupled. And nobody tells you in your quantum mechanical textbooks how to solve a large and strongly coupled quantum system. Okay, just to say it a little bit more, I think that numerics becomes hard at large N, right? So if you were going to literally do exact diagonalization or Monte Carlo, you're going to have to deal with the fact that as N gets larger and larger, the Hilbert space grows. And on the other hand, analytic methods are very limited at strong coupling. So an important tool is Monte Carlo. Monte Carlo is a numerical technique, but it has several slightly awkward features. So first of all, the physics is simplifying at large N, right? So the black hole is becoming semi-classical, Einstein gravity is becoming semi-classical, but the Monte Carlo simulation is becoming more and more difficult, right? So the physics is simplifying, but the computation is getting harder. So that seems a little bit awkward. Another very severe issue is the sign problem, right? So in the black holes that we understand from string theory, they're dual to supersymmetric quantum systems in most cases. And those quantum systems, of course, have fermions. And generically, when you have fermions, that's bad for Monte Carlo. And a third issue is that black holes can decay. And this is related to the issue of metastability in Monte Carlo simulations. So there are some problems that are ill-defined at finite N, strictly speaking, but are well-defined at infinite N. Okay? And so if you're going to try to do a Monte Carlo simulation at finite N, it's strictly speaking ill-defined. For example, the thermodynamics of certain problems is strictly speaking ill-defined. You have to go to infinite N to cure this metastability problem. And we'll see some examples of this in the talk. Okay, so the point of the large N bootstrap is that it's some sort of alternative which has its own advantages and disadvantages. And I would say that its advantages are that it can work directly in the infinite N limit, giving rigorous bounds without doing any extrapolation. And it also has no sign problem, at least in principle. So it can work with fermions. It can, in principle, even work with the Lorentzian time problems. However, there are some significant challenges, mostly on the computational side, which we will discuss. So it's not completely a free lunch. All right. So the plan for today's talk is I will first discuss the bootstrap in the simplest possible context of just the matrix integral. And then we will work our way up to more complicated systems that are also physically more interesting. So the matrix integral context, of course, has nothing to do with black holes. Hopefully, we'll get to some context where the motivation of this talk overlap somewhat with the actual results. Of course, we're not going to completely solve these quantum theories yet, but perhaps the eventual goal would be, let's say, to compute all correlation functions, time-dependent, non-time dependent, in the large N 't Hooft limit, let's say, of the D0 brane quantum mechanics. That could be some goal one day of this Bootstrap program. Okay, so any questions about the motivation before we start? Okay, so the simplest possible context which you can explain the Bootstrap in is just the matrix integral. Okay, so we have a probability distribution which has this Boltzmann form where the action is a single trace of some polynomial V. Okay, so V is some potential. We could choose it to be a quartic potential, for example. Okay, and the goal is to compute moments of this probability distribution, right? So trace m squared, trace m to the fourth, etc. Compute them as a function of the coupling G when the moments actually exist. That's the goal. Okay, and the strategy is extremely simple. Okay, so there's sort of two parts. One part is some sort of guess, and a second part is a check. Okay, so the guess part is you hand me a guess for some simple correlator. Like you tell me that you think the value of trace m squared for some value of the coupling is 0.7. Okay, that's your guess. Then I feed it through some machinery, which is the loop equations, and this machinery generates many more correlation functions. Okay, then I check positivity of the correlation functions that I computed based on your guess. And if I find that any of these positivity conditions fails, then I rule out your guess. Okay, that's the basic philosophy. Right. So if I find, for example, that trace m to the 100 is negative, then I can immediately rule out your guess, right? Because trace of a Hermitian matrix to some even power has to be positive. Okay, so let's say that in a little bit more detail. So let's consider the loop equations of these matrix models. So this is nothing but the Schwinger-Dyson equation, and it has a very simple diagrammatic form for the large N matrix models. So the idea is that we have some blob, which represents a correlator like trace m to the 6. Okay. And we follow one of the lines into the blob. When we follow one of the external lines into the blob, two things could possibly happen. One thing that could happen is that we follow the line in and it never encounters a vertex, right? So if it never encounters a vertex, it has to cut the diagram into two pieces. The reason why there can't be a leg that goes across this thing is because we're in the infinite N limit, and this would be a non-planar diagram, right? So because of planar diagrams are the only things that survive in the infinite N limit, we have a simple factorization, right? Which is written here, right? So this sum is just the sum over the different ways of splitting that blob. So this was just accounting for the possibility that we followed the line in and we encountered no vertex. The other possibility was that we encountered a vertex, right? So we encountered a vertex, and that increases the number of external lines that enters the blob, right? So that's this term. Okay, so what's the point of this? The idea is that you think of this equation as a kind of recursion relation. If you know some lower order correlation functions like trace m to the k and the lower correlation functions k minus l minus 2, for example, you can use this equation to generate a new correlation function, trace m to the k plus 2, right? So based on the initial guess, right? Let's say you told me trace m squared, I would use this equation to generate trace m to the 4th, then I would generate trace m to the 6th, trace m to the 8th, et cetera, et cetera, et cetera, right? So based on your initial guess, I can generate many, many more correlation functions, and then I can test positivity. Okay, so that's what I just said. And if any of the even moments happens to be negative, I can rule out your guess. Now, there's a slightly more sophisticated test that we can perform, which is basically the same idea. So the idea is instead of just testing the even moments, we consider a general polynomial in the matrix. Okay, so O is a polynomial in M. And we're allowed to choose complex coefficients. And then trace O dagger O has to be positive. Okay, that's just a simple generalization of what I told you, right? And this positivity is equivalent to some kind of positive semi-definite condition on the inner product matrix M. Hopefully that's clear, right? So M, right, is the inner product matrix of, it's just trace of M to the I plus J, right? And if you compute trace O dagger O, you get alpha star M alpha, right? So demanding that this is true for all possible alpha is equivalent to demanding that the matrix M is positive semi-definite, which means that it has all positive, or at least non-negative eigenvalues. Okay, so the strategy again is you tell me some guess, and then I fill out this matrix as much as I can, right, based on your initial guess. Then I compute the eigenvalues of this matrix. If any of the eigenvalues of this matrix are negative, then I rule out your guess. Okay, so here's the result of what you get when you try the simple exercise. So yeah, if you haven't seen this before, I encourage you to do it on Mathematica. You can do it in like 5 minutes. So if you find my talk boring, you can just code this up while I'm talking. So here is the idea. So we have some guess for trace M squared as a function of coupling, right? So as we increase the size of this matrix that we calculate, so we're now calculating more and more eigenvalues because we're including more and more constraints, we get a smaller and smaller region, right? So initially, this light gray region is allowed, then it's a dark gray region, and eventually we get some black region, which converges very nicely with the exact solution in green, okay? So here I've zoomed in, right? And this is only 5 by 5 matrices, so that's why it said, or maybe 6 by 6. So very quickly on your laptop, with no computation at all, basically, you can get the exact solution to many decimal places if you want. Okay, so is it clear in this basic model what we're doing? Okay, but now we can, in this toy context, explore the issue of metastability. Okay, so we previously considered a positive polynomial, right? But we could consider a polynomial which is unbounded from below. Okay, and the interesting thing is at finite n, this makes no sense, right? We cannot define a probability measure with this polynomial. But at infinite n, we can, because tunneling is exponentially suppressed, right? Tunneling is like some e to the minus n effect that goes away in the 't Hooft limit. Okay, so as you know, in the one matrix model, the solution for some correlator is an analytic function of g. So g here is the 't Hooft parameter. Okay, so it's an analytic function with a finite radius of convergence. So we can, in principle, extend that function to negative values of g up to the radius of convergence, which in this particular normalization is something like -1/12. Some number, it's not too important. So here's the boundary of the analytic solution. Okay, that's in green. And this corresponds, as I said, to unbounded potential, right? So you can ask whether the bootstrap problem makes sense for negative values of g, and what you do is you just try it. Right? So you try it, you get this nice peninsula figure, right? So again, as we increase the number of constraints, the peninsula gets smaller, and notice that the tip of the peninsula converges pretty rapidly to the actual boundary of the analytic solution, right? So if you wanted to, for example, estimate the critical value of g, right, you could do so using the bootstrap. So this shows that even for problems which are metastable, in the sense that there's e to the minus n instabilities, the bootstrap doesn't care. It can find the exact solution all the way out to the boundary of the metastable region. Yes.
Sorry, I don't know if I'm reading this graph incorrectly, but is this saying like this big shaded region is like all the allowed values?
Yeah, the shaded region is allowed, and the region, let's say in white, is completely disallowed. And yeah, as you increase the constraints, the allowed region gets smaller and smaller.
So for G positive, we saw the allowed region like basically converge the exact thing, but
Yeah.
here it's still like this big region.
Yeah, it's a somewhat big region, but these are for extremely low level constraints. So if you want to, yeah, if you actually did this on the left, I just showed you very small constraints just to make it visually easier to see. But if you want a precise estimate of this, it's not hard to generate on the laptop. Yeah, it is true that there's some non-analytic behavior in the bootstrap at g equals 0. But in practice, if you want the actual number for any value of g non-zero, you can get it very easily. G equals 0 is kind of trivial, right? Because the loop equations simplify dramatically. It's just a free theory. So that's why there's some kind of funny behavior at g equals 0. Yeah.
Sorry, is this whole graph in the limit of n goes to infinity?
Yeah, so, okay. So how did we input n? The only way we input n was large n factorization. So in the loop equations, we demanded large n factorization,
Yeah.
and that's how we input n, and that's how we do so for the rest of this talk, basically. Yeah. Another option is you could try to input finite n by imposing trace relations. I haven't done that, but Zheng and Kazakov, so one of my collaborators, Zheng Zheng and Volodya Kazakov, they've explored this idea. Okay, so slightly more complicated context now is the multi-matrix integral. Okay, so here we're considering, let's say, a two-matrix model, right? Again, we have a polynomial potential for the two matrices, and we have some complications. So what are some of the complications? One is, of course, we have many more constraints now. Sorry, we have many more correlation functions now at a fixed length L, right? So roughly speaking, there's exponentially many, there's 2 to the L correlation functions for large L, right? Because we have AB in any particular order. So there are many more variables that will enter our semi-definite programming problem, but there's also many more positivity constraints, because instead of considering a general polynomial in just one of the matrices, now we consider a general polynomial in the two matrices, and again, for the same reasons, there are exponentially many more polynomials. There's also exponentially many more loop equations. Okay, there's no different colored chalk, but imagine that we have different kinds of legs, right, in this diagram, representing the different kinds of matrices. Okay? So the squiggly is a B, the straight is a A, right? So previously, we could follow any of the external legs in, we would get the same equation. But now, generically, if we follow in this guy, we will get a different equation as if we followed in this guy or this guy, right? So the point is that now we will have exponentially many more Schwinger-Dyson equations or loop equations. So this means that we shouldn't lose hope, right? Because just because we have exponentially many more variables, since we also have exponentially many more positivity constraints and exponentially more equations, it's not obvious whether the bootstrap will work or not work. So we just, again, have to try it. If we only had polynomially many more, let's say, loop equations, then we would probably think that this approach would never work to solving these models, right? Because there are many more unknowns and so forth. But since we have exponentially many more everything, it's not clear. If you consider a simple model like this, so a generic two-matrix model is not solvable by analytic means, even in the strict Largen limit. There's a set of measure zero two-matrix integrals which can be solved analytically, and it's believed that this potential that I wrote down is not among those. So this is a somewhat generic potential. And Kazakov and Zheng managed to use the bootstrap method, which I outlined, to solve this model to very high precision. Okay, so they got some numbers for some simple correlation functions, and they computed them to like 6 digits, okay, on a laptop. And they argued also that with the same amount of computational resources, you can get more precision using the bootstrap than using Monte Carlo and extrapolating at large n. Okay, to do so, they had to use some nonlinear relaxation, which I'm happy to discuss at the end if you're interested.
Does this model have a sign problem?
This model has no sign problem, yeah. Okay, very good. So let's now discuss one step up again. So now we're going from integrals to quantum mechanics, right? So a path integral. Well, the main idea for how to improve the bootstrap to apply to the quantum mechanical setting is actually not to think of it as a path integral, but to work in the Hilbert space formalism, okay, the canonical formalism. So in this context, the simplest case would be the one matrix model, and now we don't have just x's, we have p's, and element-wise, we have some bosons which obey the canonical commutation relations that I've written there. Okay, and this model has a UN symmetry, which we can view as a gauge symmetry. So that just means we impose that the gauge generators equal 0. We could choose to impose it, or we could choose to ungauge the model, in which case we just view it as ordinary global symmetry. It's our choice. Okay, and this model, yes.
Can I ask a question if we could back up a step?
Sure.
So in these multi-matrix models,
Yes.
is there some scaling limit being taken? I mean, so
Yeah.
I guess what I'm asking is that usually the sort of the ideology is in these matrix models that you need to be near some sort of a critical point in order that the statistical
string theory. Yeah.
Well, yeah, so that the statistical ensemble is governed by large surfaces. Exactly. And so is that So when you say, okay, we bootstrapped some set of correlation functions, is that for some generic point in the space, or is that near one of these large and critical points, or what's the meaning of these estimates down at the
Yes,
bottom of the slide?
Okay, thanks. So I believe in this paper by Kazakov and Zheng, they just considered some generic points. So they literally considered this potential with like all these coefficients given here. So this is not at some critical point. However, let's say in earlier work, we'd be interested, let's say, in the behavior of this correlator near the critical point, right? That's exactly what you're discussing. And it's possible by getting a very high precision estimate of this, for example, to see the leading non-analyticity in G minus G critical. So you can see the leading non-analyticity of this curve by doing the bootstrap. Of course, this is a case where we completely understand everything, right? So, but in the two matrix model case, I don't believe it's been done, but I do think that there's actually some critical behavior in this two matrix integral, right? So if you tune the values of these couplings, for example, if you made one of these guys negative, there's probably some critical point. I think it's possible that, for example, you could realize the minimal string with, let's say, C equals 1/2 matter using this model. But I don't, to my knowledge, it hasn't been thoroughly tested using the bootstrap. But it would be some, I do think, as some sort of curiosity or application of this idea, you could attempt to find, somewhat non-standard ways of realizing the minimal string by embedding it in some complicated two matrix model that we can't solve analytically.
Or just as a test of the formalism, you could replace the commutator squared by just trace AB, where it is the standard two matrix integral.
Yes, indeed. Yes,
and
for that particular case, we did it. Yeah, for that particular, for the simple case with just trace AB, we did the bootstrap formalism, and we beautifully recover the standard results. Yeah. In that case, there's some simplicity because the loop equations simplify. When you only have a trace AB interaction, you can consider the special correlators, so you only have all B matrices and all A matrices in this pattern. And the interesting thing is that the loop equations close on this subset of correlators. So you don't have to consider a completely generic correlator with A's and B's all mixed up. You only need to consider these kind of correlators. And so the bootstrap problem is much simpler. And this is, again, related to the fact that the model is integrable. So it's also easier for us to bootstrap.
Okay, thanks.
Thanks, okay. So going back to this somewhat famous matrix model, again, we can study it sort of away from the critical point, or we could try to approach the critical point. For most of this talk, I'm just going to stick with a generic point. The reason why is, my ultimate goal is, let's say, BFSS or D0 brane quantum mechanics, and there we just work in the 't Hooft limit. We don't necessarily have to take some extra double scaling limit.
That's not the limit where it has the interesting behavior of 11-dimensional supergravity.
That's correct. That's the, so the 't Hooft limit is where we have 10-dimensional type 2A strings.
Well, it's also near some sort of correspondence transition. It's sort of like studying the theory where the temperature is near the UV cutoff.
Yes. So okay, more. You're pushing me to be a little bit more concrete. So what I really imagine is studying it in the 't Hooft limit, but in the regime where the 't Hooft parameter, the dimensionless 't Hooft parameter is large. So there we would have a reliable type 2A semi-classical gravity regime.
Oh, okay.
But I'm very happy to discuss this in more detail towards that. Okay, so the idea of bootstrapping quantum mechanics is to use the Hilbert space or canonical formalism. And what are the main ingredients? So instead of using the Schwinger-Dyson equations, we just use the Heisenberg equations of motion, if you will. And in particular, if we're interested in, let's say, bootstrapping this quantum mechanics in the ground state or in some, let's say, fixed energy state or energy eigenstate, we have a very simple equation, right? So the idea is that any time derivative of O should vanish in one of these states. That sounds very simple, but it actually generates some non-trivial equations, right? So So just to take a simple example, if we take the operator O to be trace XP, then the fact that its time derivative vanishes tells us that this linear combination of one-point functions has to vanish, right? And we can think of this, if we like, as a relation between a higher point correlator like x to the fourth and some lower point correlators, just like before. Okay, so again, the idea is that we just enumerate a huge number of operators and demand that all of their time derivatives are 0 in the ground state or in some excited state. And by doing so, we generate a bunch of relations between correlation functions. And again, we can apply our strategy of guessing some unknowns and then trying to rule out those guesses. Of course, when I say guess and check, I don't literally mean that's what you do. I mean, you use semi-definite programming, but that's just a fancier way of guessing and checking. And the second ingredient is positivity, right? So here we replace positivity of the measure with just positivity of Hilbert space. Okay, so that just means that, for example, trace O dagger O in any energy eigenstate is positive. Right? Now, to prove this, note that you actually have to consider the gauge non-singlet sector. Right? So in order to show that this is the sum of squares, you have to think of this in the gauge non-singlet sector where I cut the Hilbert space here. Right? But, okay, we're allowed to do that. And never we conclude that we can find some matrix again of inner products. So a matrix of inner products defined in such a way, such that all of its eigenvalues have to be positive or 0. There's one other positivity requirement that we're going to consider, which is sometimes called ground state positivity. Okay, and ground state positivity is an extremely physical requirement, which just says that if you perturb the ground state, it has to increase the expected energy, right? So the idea is that you consider this commutator O dagger, commutator of H with O, right? And this is two terms. This is the first term, this is the second term. The second term, right, H acts on the ground state, so you just get E of the ground state. Okay, so then we just divide this equation by O dagger O. If we divide this equation by O dagger O, which is positive, right, we would just get E of the ground state, and then this thing here would be O dagger HO divided by O dagger O, which is just the expected value of H, right? So all we're saying is that the expected value of the Hamiltonian in some state, which is O acting on the ground state, that energy has to be bigger than the ground state energy, which is a very physical requirement. Okay, so we define some matrix Nij, which is this matrix N has to be positive semi-definite. So this is true just for the ground state. It's not true for some excited state. But this is how we can input, for example, the fact that we're interested in some particular correlator in the ground state of the quantum mechanics. Okay, so let's do that for the simple one matrix model. Again, we will get.
Sorry, just the last condition. It's an assumption, or isn't it? Is it a defining property of the ground?
Yeah, it's a defining property of the ground. Okay, yeah. Maybe it's literally the condition that if we define a state like this, so this is the ground state. So omega here is the ground state. O dagger is any operator acting on the ground state. Let's call this state psi. Positivity, this positivity is just a statement. Yeah, so it's an extremely simple condition, right? Okay, so imposing these ingredients, we will again get some constraints. So for example, we can make these 2D plots of trace x squared versus something like the ground state energy, for example. And we get some islands in the allowed regions. And as we increase the number of constraints, the islands get very tiny, right? So this was originally some, let's say level 6 plot, then we, maybe level 4 plot. Then as we increase the number of constraints, we get a very tiny island. And eventually our islands, just on a laptop, you get islands which have like, let's say 6 decimal digits for simple observables. So again, this just shows that the method works, and we can compare to the exact solutions which we get from the n-free fermions. Now, something that's a little bit more interesting is we can input, we can attempt to bootstrap thermodynamics of these large n quantum systems. Okay, so one can do this using the so-called EEB inequality. And this EEB inequality was first discussed in some very old work, like in the 70s by Iraqi and Sewell. But recently there's been some interesting developments about practically using it as a bootstrap problem. So this was done in some recent work by some condensed matter people, Fauzi Skelet, and also by Minjay and collaborators. And the condition is a very interesting condition. So the right-hand side looks like what we've just were talking about, right? This commutator of this O dagger H commutator O. This was basically delta E, right, which we just discussed. So this is like beta delta E, and this log thing kind of looks like an entropy. So you can think of this as delta S, right? So this is like a condition that says delta S is less than beta times delta E. So that's like saying that the free energy should increase, right, under generic perturbation. So for the ground state, the condition was that the energy increases under generic perturbation. The idea is that this inequality is roughly like saying that the free energy should increase when you perturb the thermal state. Okay. But the interesting thing about this equation is that beta enters, right? So we can input the value of beta into the bootstrap by imposing this inequality. Okay, so instead of imposing this condition, which was rather simple to derive, we impose this condition, which depends on beta. So we will meet this inequality later. But I just wanted to show you a plot from Cho, Gabai, Sandor, and Yin. So they bootstrap the thermodynamics of the ungauged one matrix quantum mechanics. So this is the one matrix quantum mechanics that I just was discussing, but ungauged. So you do not impose the gauge singlet constraint. And there, the thermodynamics is not known to be analytically solvable. But using this bootstrap method, one is able to calculate, let's say, the energy as a function of temperature. So this black line is the bootstrap result. And there's some low temperature and high temperature result that's known analytically, but let's say for intermediate temperatures, we don't know how to compute it. Okay, on to BFSS. So BFSS is another name for the D0 brane quantum mechanics. Okay, so this is the super Yang-Mills theory in just one dimension, right? You can get it from reducing 10-dimensional super Yang-Mills, n equals 1 10-dimensional super Yang-Mills to 1 dimension. So it has 16 supercharges and 16 corresponding fermions, which transform in the spinor of SO9. And it also has some bosonic matrices that transform in the vector of SO9. Okay, and it has a lot of interesting physics in it, which I won't have time to review. But a lot of what we know about it from the matrix side is due to some heroic Monte Carlo simulations by these people. Yeah, as I was saying, there's a TÜV limit in this model. So the TÜV parameter in d dimensions, where d, let's say, is less than 3 plus 1, right? So in less than 3 plus 1 dimensions, g squared Yang-Mills has units, right? Unlike in 3 plus 1 dimensions. And it has units. So in order to make a dimensionless TÜV parameter, we have to multiply by some length scale or some time scale, right? So the natural thing to do is to consider the theory at fixed temperature and to consider a dimensionless TÜV parameter, which is formed by g squared times n times beta cubed. And then the TÜV limit is to take n goes to infinity, holding this parameter fixed. Okay, and this parameter could be big or small. So as I was answering Emil's question, if the parameter is big, we have a description in the dual quantum mechanics, which is a black hole, which is described by semi-classical type 2a supergravity. Okay. So if we make this parameter small, it becomes a stringy black hole. And we could discuss this in a lot of more detail. Basically, this is the Penrose diagram of this black hole. The thing that's it looks a little bit like the ADS black hole. The difference is that there's a singularity at the boundary. And that's because the Yang-Mills coupling constant is a relevant coupling constant in low dimensions, right? So in the UV, the theory is free. And because the theory is free, it couldn't possibly be described by some sort of Einstein gravity-like description. So it becomes kind of singular. Yeah, so the only thing you have to remember for this talk is that g squared Yang-Mills has units, and in particular that it's a relevant deformation in quantum mechanics. So only at low energies do we get a strongly coupled theory, which is well described by Einstein gravity. Okay. Okay. So how do we bootstrap this quantum system? Well, I'll be a little bit brief. The basic idea is instead of imposing the Hamiltonian equations of motion, we impose the supercharge equation of motion. So this basically says that we take the supercharge, which has this alpha index. We have to find another operator which has an alpha index if we want to make an SO9 singlet, right? So the idea is that only SO9 singlets can have expectation values in the ground state. So we have to enumerate all possible operators O alpha, which transform as a spinor under the SO9. Okay. And of course, this means that O alpha is a fermionic operator. So we enumerate all possible fermionic operators that transform as spinors. That's one step. Another thing that we have to do is we have to define some way of cutting off the bootstrap problem, right? So when I say cut off, I don't mean that we're doing something non-rigorous. I just mean we need to choose which constraints we want to impose because there are obviously infinitely many constraints. So we have to organize which constraints we want to impose in some way, and we choose the following way. So we choose a way where we define a level where x is equal to 1. So the level of any operator made out of x, each x counts as 1. The fermion has weight 3/2, and momentum has weight 1. And the reason we choose this is because acting with the supercharge on x gives us psi, right, which increases the level by 1/2. And then acting again with the supercharge on psi gives us p, which again has a level that's 1/2 bigger than this. So the idea is that in this method, we can systematically enumerate all possible constraints up to a certain level, and then systematically increase the level to see how the constraints improve. The kinematic constraints, again, as I said, all SO9 non-invariants have to vanish in the ground state. Another thing is that there's cyclicity of the trace. That's actually how we input large N. And we have the SUN gauge constraint. So the kinematics is actually the most technical part of the bootstrap. Based on what I said, it sounds totally trivial. And conceptually, it is trivial. But technically, it's a little bit non-trivial. So I thought I would just spend one slide explaining what we do. So the idea is we want to consider some positivity matrices, like this M. Okay, so if I cut this matrix in half, you see that this is some operator, and this is O dagger, basically, right? So this is some giant positivity matrix. It's a positivity matrix with 16 squared times 16 squared entries, right? We don't want to build that matrix explicitly, right? So we're going to use some kind of group theory, right? And the idea is that, well, we can just enumerate all possible SO9 structures, right? So we have 16 times 16 is equal to these, the antisymmetric tensors, right? And each of those has to be paired up with another antisymmetric tensor in order to make a singlet. Okay, so in equations, that says that this matrix has to have this following form, right? Where all of these gamma matrices describe the fusion of the spinor indices into some antisymmetric tensor. Okay, so using group theory, we've reduced this giant matrix into just 5 unknowns. So these are just the 5 unknowns that could parameterize the SO9 invariant possible. Using SO9 invariants, we've reduced the possible structures of M to the simple form. Okay. Now, if we use cyclicity of the trace means we consider this thing, right? And we rotate psi, we bring psi around, right? When we do so, we have to decompose the same correlator in a different channel. So you see, this diagram is basically just a rotation of this diagram. But when we do so, we have to decompose the T channel into S channel blocks. So that's given by some fusion coefficients, right? These are the 6J symbols for SO9. So using this equation, we can actually reduce these 5 unknowns to just 2 unknowns. Okay, so this was what was allowed by SO9 symmetry. Then using cyclicity of the trace, we will get another expression for M, which is basically the T channel decomposition instead of the S channel decomposition with the same coefficients. Okay, so then we'll have some linear equations. Solving those linear equations will reduce the 5 unknowns to just 2 unknowns. So this is very similar to the conformal bootstrap, if you like. So these A's that appear are basically like the squares of OP coefficients, right? So you have some representations R1, R2, and they confuse into some R3 here, which is then interchanged, right? So these A's are then the things that are positive. They're like the squares of OP coefficients. So at the end of the day, what we do is we do all this group theory, we get a bunch of A's, and we have some positivity conditions on A's. And that's how we work with this problem. So what is the point of all this? The point is the following. If we were to brute force enumerate all possible symbols involving x1 up to x9, psi1 up to psi16, we'd make a huge mess, right? We'd have some enormous bootstrap problem with huge numbers of variables, right? And we cannot possibly handle that even numerically. So you have to do this group theory stuff to reduce the number of variables to just group invariants, which you can actually manage on the computer. Okay, so after we do all that, which is a little bit fun, we can make some plots. So here's the plot now. We see the constraints for some allowed regions. So here I'm applying the kinetic energy, so just trace p squared as a function of trace x squared in the ground state. Okay, so I've imposed the ground state condition by demanding that the supercharges annihilate the state. Okay, so as you increase the number of constraints, you get a smaller region. That's not surprising. What's kind of cool is that you get some peninsula with a kink in it. Okay, so as once you get to level 5, you already get the peninsula, and there's a kink at the tip of the peninsula. And this kink actually seems to be converging somewhat as we go up in level, right? It seems to not be moving too much. So you might guess, using the bootstrap logic, which is nothing but lore, really, that the exact solution is somewhere close to the kink, right? That's what the bootstrapper would say. You're not supposed to ask why. Okay. So if you believe that, then you can also ask the Monte Carlo people what are their values for trace x squared and k after a suitable extrapolation. So, what you find is that the Monte Carlo result is actually pretty close to the tip of the peninsula. And actually, that's not totally trivial because the Monte Carlo people actually don't treat the sign problem correctly. So this, they don't treat it rigorously. So what I mean by that is, this is a quantum mechanical system with 16 fermions. It has, in principle, a sign indefinite determinant once you integrate out the fermions, right? And indeed, there's a sign problem at finite n. But they seem to notice that the sign problem is not so severe at large n. At least that's the claim. And so what they do is they just literally put an absolute value in front of the determinant and hope that that's okay. Okay, so that's how they do the Monte Carlo simulation. And they have some evidence, I think, that the sign problem is not so severe. But it's not entirely clear to me, at least, if it's suppressed by some large parameter or not, or whether it's just happens by coincidence to be a small effect. So one thing that's interesting is that the result is pretty close to the bootstrap kink. And therefore, you might believe it a little bit more. Or you could say that perhaps with very high precision bootstrap in the future, maybe we can rule out their result. Maybe we can shed light on this sign problem.
Henry, is this with the gauge constraint, the Gauss law imposed? Or?
Yes, with the Gauss law imposed, yes, and all the supercharges imposed. Yeah, another thing I would say is the following. So yeah, we're doing a ground. Why did we choose the ground state? Well, one reason is the dimensionless TUF parameter m to beta cubed. For the ground state, of course, beta is infinity. So this is like a very strongly coupled problem, right? The problem of computing correlators in the ground state is a very strongly coupled problem. And therefore, it's kind of our advantage. The Monte Carlo group, they can do smaller values of the TUF parameter more easily because there your Euclidean time circle is smaller. So they have a little bit of a difficulty extrapolating to a large TUF parameter where you make contact with the gravity interpretation, et cetera. Okay, here's another plot. I'm just plotting a different observable, which is trace xi, xj, xj, compared to trace x squared. And there's some interesting behavior in this plot. As you see, there's some qualitatively new information that you get at level 5, where this thing becomes vertical. And then again, some qualitatively new information at level 7, where instead of a perfectly vertical line, you get some kind of a smooth curve. Okay, that's nearly vertical, but not quite vertical. And again, there's some kind of kinks in these curves. So you might guess that the true value of trace x squared is not quite the vertical asymptote, but somewhere near this, this kink here. Okay. The interesting thing about this plot is that this gray curve was actually produced by Polchinski in 1999. He didn't quite phrase it this way. And in fact, well, up to some factors of 2, he basically got this curve. And in my understanding is that in 1999, Polchinski derived this curve using virial theorem arguments, essentially to try to settle the debate of what the size of the bound state wave function is in BFSS. So the original BFSS paper actually gave two estimates for the n scaling of the bound state wave function. So it wasn't so clear what the size of the bound state wave function is. Even its n dependence was unclear. And Polchinski showed that there was a lower bound on trace x to the 4th, which corresponds to this point, thus ruling out an extremely tiny bound state. So in an extremely tiny bound state, let's say a bound state that was suppressed by powers of 1 over n in this normalization, was somewhat suggested by the M theory picture. So the M theory picture is that you have a tiny M theory region sort of near the center of this geometry, whereas the type 2A TUP scaling argument was that the bound state region should be the size of the type 2A region, which is much bigger. Okay, so Polchinski's result showed that the bound state actually scales like the type 2A region. The size of the bound state scales like the type 2A region and not the M theory region. Okay, the cool thing is that if you look back at Polchinski 99, you will see that his argument is a bootstrap argument in the sense that the ingredients that he used to derive this bound are exactly the same ingredients that I was talking about. Okay, so here we've just sort of generalized what he did by including many, many more operators and using supersymmetry in a more systematic way. Yeah, these results can also be generalized to finite energy, where we can discuss the dependence on the touch parameter, et cetera. Yeah, I want to not dwell on this too much though, so we can get to the time dependent stuff. I just wanted to mention, you could ask, so I had some peninsulas, could we get islands? Right? We obviously want islands and not just peninsulas if we're bootstrappers. And I don't know the answer to that. I suspect it's yes, but in a different context, I do know the answer. And that context is in less supersymmetric models. So in particular with Zheng, we studied the d=9 version of this model, which is just sometimes called bosonic BFSS. So you just throw away all the fermions. And in that model, you can make similar plots. You again get peninsulas. So that's this orange curve, it's some peninsula. And then if you go to high enough levels, you get an island. So in fact, this is a level 10 result, which is 1 level higher than in the previous plot. So at 1 level higher, you suddenly jump to an island. And the island is not that far from the tip of the peninsula in some sense. And also, you can compare with Monte Carlo and also the large D expansion. So this bosonic model has some nice vector-like limit where you can compute. And for d=9, you see that the exact result is not so far from the large D result. So the exact result, well, our islands are so tiny, as you can see, that we can get to many digits of precision.
Doesn't that bother you though? I mean, I would have thought that if you just make the thing entirely bosonic, that the connection to gravity would be largely lost.
Indeed, I don't think that there's a nice gravity dual of this model. But yeah, as a bootstrap exercise, it's somewhat, well, potentially informative. But yeah, indeed, yeah, I don't know what the gravity dual of this model is.
Okay, but you just say, okay, as an exercise in understanding some large N matrix dynamics. It's,
yes, yeah, some yeah, strongly coupled the large N matrix dynamic. Yeah, there is an interesting phase diagram of this model. It has some kind of a Hagedorn transition and also a Gross-Witten-Wodia transition. Here we're in the very low temperature phase. So we're in the sort of confined phase when we're making this plot. Yeah. So I would love to combine these techniques and let's say make some plots of the thermodynamics for BFSS. And for example, test the prediction of the thermodynamics from the type 2A black hole. I think that would be a very clean thing that we could imagine doing by combining some of the ingredients that I have discussed. I don't have such results, but I just want to say that in principle, a high precision estimate of those kind of things would teach us something. So first, we would just check that we get general relativity. So we get the area over 4G Newton that Hawking wrote down. And then we would get some alpha prime cube corrections to that formula. So that those would come in as finite TUF parameter corrections to the thermodynamics. And even the leading alpha prime cube correction is currently unknown. Right? So you would need the full nonlinear completion of alpha prime cubed involving Ramon gauge fields in order to be able to compute this. So we don't know it even from smooth theory. So in principle, by doing this bootstrap, we could learn something about the alpha prime cube corrections. Okay, let's now go to the time-dependent problem. So I've so far just been discussing thermodynamics and one-point functions. You could also discuss the next simplest thing, which would be two-point functions in Euclidean signature. Okay, so what are the constraints? Again, we will have some matrix M, right, which is an inner product matrix OI, OJ, but now we put some time, Euclidean time separation between the 2 points. Okay, and this matrix by reflection positivity is positive semi-definite for all times tau. So that's one positivity constraint. And we also have some other constraints. So again, we have the Heisenberg equations of motion. So now the Heisenberg equations of motion just tells us that the time derivative M is equal to some linear combination of M, which is determined by the commutators, right? So I've just given the commutator of H with O some new name, which is D. So I've expanded the commutator in some basis OK, and I've defined some matrix, which are the coefficients in this expansion. So the Heisenberg equations of motion is just d tau M is equal to minus md with these conventions. And then there's one other ingredient, which is that the ground state or the thermal state is time translation invariant, right? That means that you can differentiate either this guy or this guy, you get the same answer. So that tells you that d dagger M minus md is equal to 0. Okay, so extremely simple ingredients, right? Hilbert space positivity, equations of motion, and time translation invariance. And the fourth ingredient is the ground state positivity, as I was discussing here. Now, again, the only difference is that we have some time separation, but the same argument goes through. So you perturb the operator, the ground state now with a time-dependent operator, and its energy must increase. So that defines some N matrix, and it's related to the M matrix by this D, right? And that's because, as you see here, the commutator with H, which came into the ground state positivity, can be interpreted basically as a time derivative. So that was this D matrix that we discussed. Okay, so these are the conditions for our bootstrap problem. We want to derive some bound, let's say our lower bound on some observable, right? So the observable could be a linear function of this inner product matrix. For example, it could just be in some simple quantum system, it could be just trace xt x0, some 2-point function in some matrix quantum mechanics. This would be some matrix element of this big positivity matrix. And the particular time that we care about, we put it into the bootstrap by putting in some capital T. So we're interested in this correlator at some particular time. Right? We want to derive some bounds on this correlator at some particular time, subject to these constraints. Okay, so far I've done absolutely nothing. I've just told you, I basically just restated textbook quantum mechanics. And if I could solve this problem, well, I would basically be able to solve the quantum system, right? If I could solve the Heisenberg equations of motion, I wouldn't need to do bootstrap. I could just solve the system. So at this level, I've done nothing. The interesting thing is to go to the dual problem. Yes.
Sorry, what was the point of the tau over 2? Like you had like tau, then 0, then tau over 2.
I just used time translation invariance to write this as tau over 2 and this 0 as minus tau over 2.
Right.
And then it was clear that I can think of this as a state where I perturb the state by an operator at Euclidean time minus tau over 2, and then the ket is with the minus tau over 2, the bra is with positive tau over 2. So that's why I shifted the arguments, just so that you could see that it has this form.
It's not essential.
Well, yeah, in order to prove this inequality, I have to shift the argument from tau to tau over 2. In this inequality, I need the bra to be the conjugate of the ket. So in order to, this first line doesn't have that manifest form. The second line has that manifest form. It's just a minor detail, yeah. Okay, so this is what we would like to optimize. But in this form, as I said, we've done absolutely nothing. So the trick in solving this problem is to go to the dual formulation. Okay, so what is the dual formulation? Well, it consists of 4 parts. First, we write down the action, then we integrate by parts. Then when we integrate by parts, we impose the equations of motion for M. Sorry, after integrating by parts, we impose the equations of motion for M. And then we will eliminate the certain Lagrange multipliers. So let me just show you what I'm talking about. So once again, we want to minimize this thing, trace O hat M, where O hat is some operator that we can choose. Okay. So what we do is we write down an action. So we want to minimize this thing, trace O hat M. subject to some constraints, right? So we introduce some Lagrange multiplier for each of the constraints that I told you about in the previous slide. So let me just focus on. So let me just focus on the constraints that don't involve n. So let's just focus on this capital M, these three equations, right? So this was reflection positivity, this was Heisenberg equation of motion, this was time translation invariance.
Might need to click on the screen to get the click of the webcam.
Started an annotation. Okay, it's working again. Great. So those were the three constraints. So here we see a Lagrange multiplier that imposes the equations of motion. So lambda d here imposes that basically dm is equal to d tau m. Right. So that was just the equations of motion. We have another equation lambda a which imposes time translation invariance. And we have another Lagrange multiplier which just says that m should be positive semi-definite. So those are the three Lagrange multipliers corresponding to the three constraints. Right. Then we integrate by parts. Okay, so we integrate by parts, that just changes the sign of this thing, and it generates some boundary term. So this is the boundary terms that we generate. Okay, and now we vary with respect to m to get some equations for lambda. Okay, so now we have this simple thing here, right? We vary with respect to m. We will get some equation here, and also some boundary condition here. Okay, so doing so, we got these equations. So we got so this equation came from varying with respect to this capital M, right? This constraint here, O hat equals lambda d over t, comes with respect to varying with respect to M of capital T. Okay, and finally, we get an equation that says this is equal to, well, okay, one more step. So this equation actually says that this combination is equal to lambda M, capital lambda M, right? So this capital lambda M, at this level, if I don't say anything further, it's totally vacuous because the right-hand side would be just equal to some matrix. So we had no constraint at all on this combination. But then we remember that this capital lambda M was imposing positivity of M. So that means that when we go to the Lagrange multiplier, we have to think of lambda as a positive semi-definite matrix itself. Okay, so the final condition that we derive is that some combination of the Lagrange multipliers is positive semi-definite. Okay, why did I go through this? So we have the dual formulation now. It's written in terms of Lagrange multipliers instead of M. But the most important thing is that the Heisenberg equations of motion that we wrote down initially have been converted into inequalities of motion. Okay, so that's very important, right? In this equation, we no longer have any equality constraints. The only equality constraint is some sort of boundary condition. The bulk of these equations, so this thing all depends on time. This thing is no longer an equality, but it's an inequality. Okay, and that's important because it means that we don't have to solve any equations. We only have to solve inequalities. So that's a bootstrap problem that's much more manageable, right? So the idea is that we're trying to find some random functions, basically, that satisfy these lambda constraints. So if you find any garbage function off the street, and it happens to satisfy this equation, right? You immediately derive a bound on the thing that you actually cared about. You derive a bound on this correlator that you tried to bound, okay? And this is true even if you only choose some finite basis of lambdas, right? As long as you can show that you satisfy this constraint, you immediately derive a rigorous bound on the actual continuous time correlation problem. So we don't have to discretize time or introduce some sort of uncontrolled systematic error. So just to be a little bit more concrete, you take a basis of positive functions phi I. So these are functions that are positive everywhere. And you consider an ansatz for the Lagrange multipliers. So that these Lagrange multipliers were all matrices, okay, because the original problem involved matrices. And you take this ansatz, you plug it into the equation, assuming that the derivatives close within this ansatz. Okay. Assuming that, you now get this dual formulation, right? So here, just these coefficients AI are just the coefficients of the Lagrange multipliers in the spaces of functions. This problem is a completely finite, semi-definite programming problem, right? So this is a problem that you can put on the computer very easily, and it's a completely finite problem. As long as you can find some matrices which satisfy these positive semi-definite constraints, you're done. You've satisfied the conditions for all continuous time tau. Okay, so the upshot is you started with a problem that was in continuous time that you couldn't solve that involved equalities. You did some magic, and you ended up with a finite problem that didn't involve any continuous time tau and just involved some matrices that have to be positive semi-definite. Somehow, by solving this problem, if you can solve it, you would derive some rigorous bounds on the original problem, even though you could have chosen any particular basis that you wanted. So I think that this is a sort of a neat result because naively, you might have thought, well, in order to solve these time-dependent problems, I have to go to the path integral formalism. I have to discretize Euclidean time and put it on a lattice or something like this. That's not what we're doing at all. Somehow we're able to, overcome all of these continuous time issues directly. And
Yeah, can I ask, but you are truncating the set of operators?
yes, we are truncating the set of operators.
But time evolution doesn't keep you in that subspace.
That's
So
very
your
good,
M
very
matrix is taking you out of it.
Yeah, that's a very good question. So I was a little bit fast about this. So we have a way, the short answer is we have a way to rigorously treat this. So it's similar to even in the one-point functions, right? If you keep taking commutators of O, eventually you will generate some operators that are not in the subset that you want to consider. So what you do is you delete all those equations that involve commutations with, you take any equation where the commutator of O with the Hamiltonian leaves the subset that you want to consider, and you just delete them. So then you still get some rigorous bounds. So
It's still positive. There's still a notion of positivity.
yes. So the idea is that that's a weaker condition than the full set of constraints, but it's a weaker condition. It's still a rigorous thing. If you can rule out a point on weaker conditions, then it's obviously true that when you impose more conditions, that point will still be ruled out.
And you can always do this, or you need to find a subset of operators that kind of keep close.
Yeah, so it's important to organize your operator in some kind of systematic way. So using this level notion that we were discussing, it's a good way to organize the operators because the level can at most change the operator by 1. So taking the commutator of the Hamiltonian with that operator changes the level by at most 1. So the bulk of your operators are safe. There's just some boundary of operators which you need to worry about.
And worry about is being done in a kind of rigorous way.
Yeah, it's literally just taking any equations that you that take you out of the subset and just deleting them. That's the approach. Okay, so
So if you have some sort of time dependent information about the time dependence, can you process that into some information about the spectrum?
yeah, that's a good question. So in principle, yes. I guess in practice, the question is how practically can you do it? Well, maybe I can continue and then we can discuss a little bit more. So I think the next slide will partially address. So one way of addressing this would be to compute the thermodynamics. That tells you something about the spectrum, right? So we can do this again with what I just said. We just delete the ground state positivity constraint and impose KMS condition. Okay. So then we redo the whole dual problem formulation. I won't bore you with it, but you can imagine. Now, one nice thing about this formulation is that we can actually give a very quick derivation of the EEB inequality that I just discussed a couple slides ago, right? So the derivation goes like this, right? So first consider any log convex function G, okay? So I assume for the second that G is log convex. Then just by definition of convexity, log of this thing has to be greater than or equal to beta times the derivative, right? This is just the derivative of the log, right? So this is just what it means for a function to be log convex. So now I would like to argue that the 2-point function, the thermal 2-point function, is log convex. Well, to do that, I just consider the positivity matrix M, where M is consisting of two operators. It's the inner product matrix for two operators, O itself and the commutator of the Hamiltonian with O. Okay, so that gives me a 2x2 matrix. And demanding that the matrix is positive semi-definite means I first demand that G is positive, and then I demand that the determinant of this matrix is positive. The determinant of this matrix is G double prime minus G prime squared, right? And because G is positive, I can also divide that quantity by G squared if I like, and that quantity will still be positive, okay? And then I recognize this combination as log G double prime. So the fact that log G double prime is positive means that this matrix, that this function G is log convex, right? So that means that this G, which is the 2-point function, satisfies this inequality, right? So this inequality was log of G of beta over G0, and G of beta, just by some simple algebra, you can convince yourself that G of beta using the KMS condition is nothing but this O bar, right? Whereas G of 0 is O bar O, right? So G of beta will be O bar, G of 0 will be O bar, sorry, O bar O. And this thing here will be the commutator of the Hamiltonian with respect to O times O dagger, right? So as you can see, perhaps this gives you exactly the EB inequality, right? So this was the EB inequality that I went on and on about. We just derived it from the time-dependent bootstrap in about 3 lines. So this thing here, right, was the change in energy. This thing was what I was calling like delta S. Okay, so in particular, we can we have derived now from the time-dependent bootstrap the EB inequality. So that must mean that the time-dependent bootstrap is at least slightly stronger than the EB approach, right? And indeed, we can check that. Unfortunately, this didn't render correctly. Yeah, it seems fine on my computer, but there's some shaded region here that we get from the time-dependent bootstrap that is slightly smaller than the results that you get from EEB. So Minjay collaborators derived these EEB results for, let's say, some simple observable as a function of beta. And then with their time-dependent results, we get some shaded region, which unfortunately you cannot see, that is slightly smaller than the region in between the blue curves. And using the same technique, we can derive constraints on the energy as a function of temperature. So that does tell you something about the spectrum. Yeah, just real quick, based on what I said before, so I said that this function G, based on these time-dependent bootstrap, we have concluded already that it's log convex. That means log G double prime is greater than or equal to 0. The function that saturates this inequality is the exponential. The exponential in tau saturates this inequality. So we immediately derive a very trivial lower bound, which says that G has to be bigger than or equal to some decaying exponential, and we can actually calculate the coefficients rigorously. So we have some rigorous bound for any quantum system, basically, that the 2-point function has to saturate. And we can see, so that's what you get analytically. Okay? Now we do the numerics. The numerics, of course, are going to be better than the analytics because we can consider many more operators, right? So analytically, I was just doing this by hand, but I was only considering basically 2 operators. Whereas numerically, we're now going to consider many more operators. So we're going to get better constraints. And here's what we see. So here's the thermal 2-point function. Okay, this gray region is the allowed region at some low level. And actually, the boundary of this curve is just the decaying exponential. Okay, because of the KMS condition, we also have an increasing exponential from the right-hand side. So there will be 2 exponential curves. They intersect at this point, and you see it's a very sharp point. So this is actually the optimal bound that we derived from the numerics. Okay, it's not totally trivial that we got the analytic result from the numerics because we are using some spline basis, right? So we're using some finite basis of functions, and only when that basis of functions is sufficiently rich do we actually converge to the analytic prediction. Okay. Then, of course, as we start increasing the number of constraints, we get a better and better bounce. So you see already at level 6, we get some very tiny region for this thermal 2-point function. Okay, this is for the anharmonic oscillator. So this is not a particularly complicated quantum system, just the anharmonic oscillator. But nevertheless, with the very modest computational resources, we can compute the thermal 2-point function to pretty high accuracy. Then we discussed the one matrix model. So here is a plot of the 2-point function from the bootstrap for the infinite n matrix quantum mechanics. And you see that once again, we have some gray region that's allowed. Then once we go to higher levels, we get an island, right? So there's some finite region that's allowed for each particular time tau. And then as we go up in level, we get some very, very tight, tiny little islands. So we get some decaying exponential. And this allows you to actually estimate the adjoint gap in this model. So this is the adjoint correlator in the sense that we take the ground state, we perturb it by some adjoint operators, so that takes us into the adjoint sector. And then the exponential decay here measures the adjoint, the leading adjoint gap. So that's another, yeah, I should finish. Okay, basically I'm done. So, so some future directions are going into Lorentzian time. This was already partially discussed by these authors, which actually had this very nice idea of using the dual formulation in the first place. So we owe a lot to this paper, I think. There's also going to higher point functions, right? So we would like to study 4-point functions, talk about, out of time ordered correlators, et cetera, et cetera. I think another direction is, of course, studying BFSS in much more precision, getting islands for BFSS, trying to, for example, study the quasi-normal modes of BFSS, study the quasi-normal modes of the ungauged matrix quantum mechanics, especially because that model has also, it's been speculated by, for example, Kazakov and Kutsov and others that this model might have something to do with some kind of Euclidean cigar geometry. So it would be nice to probe those kind of conjectures using this technology. And finally, studying other large N lattice systems. So for example, Yang-Mills with the data term we were discussing lunch. In principle, these kind of systems with the sign problem can be addressed using this Hamiltonian bootstrap formalism. So thanks a lot for your attention.
Any further questions for him? Thanks.
So in real time, you wouldn't have this positivity, I guess, that you had.
Yeah, thanks. Yeah, so we would not use reflection positivity, but we think that there may be a way of still getting a bootstrap problem where we consider essentially a 2-state problem. So the idea is that you can either perturb by a Euclidean time operator or by a Lorentzian time operator. And then that combined problem will give you Lorentzian time correlators on the off diagonal of some big matrix. And on the diagonal of that matrix will be Euclidean correlators. So it seems hopeful that by some method like this, we could discuss Lorentzian time physics. Also, yeah, these guys discuss directly Lorentzian time physics, but in a somewhat different method than what we did, because they don't input the state via some Euclidean preparation. They input the state by telling you what the moments of some simple operators are. So that's another way you could attempt to do Lorentzian time physics. And they did this problem. The thing I think is when you input just some limited knowledge about moments of some observables, there are many, many, many states which are consistent with that data, right? So even apart from the technicalities of the bootstrap, there are many, many states which are consistent with your initial condition. When you evolve forwards in time, you're going to get really big bounds because there are many possible trajectories that are consistent with your known initial data. Whereas I think with the Euclidean input, you more naturally pin down the state. So, yeah.
Okay, let's thank Henry again.
Sorry.
No,